Now that we understand the language of complex vectors, we can use that language to construct a theory of complex matrices. So an m by n complex matrix is an m by n array of complex numbers. So for example, here we're looking at a perfectly good 3 by 2 matrix, but the entries in this matrix are complex numbers, some of which are not real numbers. Here's another perfectly good matrix. This one is a 2 by 3. Again, the entries here are complex numbers, and some of them are not real numbers. And finally, here's a 2 by 2 matrix. The entries here, remember, are all still complex numbers, but they have each one of the entries in this third matrix happen to also be real numbers. Remember, every real number is a complex number, but not every complex number is necessarily a real number. So if we look closely at how we're defining complex matrices, we can reformulate everything we've done so far. So let's say we're studying an m by n matrix A, and we're studying another vector v in c to the n. So the setup here is that the number of coordinates inside of this complex vector is the same as the number of columns of our matrix. We can define the matrix vector product of this matrix with this vector in exactly the same way that we defined matrix vector products previously. What we do is we construct a linear combination of the columns of our matrix, where the scalars we're using to scale each of the columns come from the vector v. So in our matrix vector product, what we're doing is we're taking the first coordinate of v and multiplying by the first column of A. Then we're taking the second coordinate of v, multiplying by the second column of A. And then we keep doing this until we get to the last coordinate of v and multiplying by the last column of A. And then we sum all of those terms together. And it's important to point out that if we start with an m by n matrix, we've now constructed a theory for taking a vector in c to the n and multiplying by A. And each one of the columns of A is a vector in Cm. So this linear combination is another vector in Cm. So A multiplied by this vector is a new vector in c to the n. This is exactly how matrix vector products worked previously, except now we're allowing for the entries to be complex numbers that aren't necessarily real. So just like before, we can view every m by n matrix as a machine. When our matrices previously had real entries, we viewed an m by n matrix as a machine that goes from Rn into Rm. We can now view our complex matrices as machines that go from Cn into Cm. So let's look at an example. Here we have a 3 by 2 complex matrix. And we're going to multiply by this vector in C2. Well, to do this, we should rip out the two columns of this matrix and scale them individually by the coordinates inside of our vector. So we're going to take a linear combination with two terms. For the first term, we're taking the scalar I plus 1 and multiplying by the first column of our matrix, which is I negative I. And then for our second term, we're taking the second scalar inside of our vector, I, and multiplying by the second column of our matrix, negative I minus 1, I plus 1, and 2I minus 1. When we do the arithmetic here, what we're doing is we're taking I plus 1 and multiplying by each I, negative I, and I. That gives our new vector, I minus 1, negative I plus 1, I minus 1. And then when we multiply this second column, negative I minus 1, I plus 1, 2I minus 1, by the number I, we get negative I plus 1, I minus 1, and negative I minus 2. Now we add our vectors together and we end up with the new vector 0, 0, negative 3. So we took our 3 by 2 complex matrix, we multiplied by a vector in C2, and the result was a new vector in C3. So what other sorts of things have we been doing with matrices? Well, one important operation that we've encountered is the operation of transposition. Well, in the world of complex matrices, we almost never transpose a matrix in stop. We usually follow transposition by conjugation. So when we're working with complex matrices, we almost never transpose. We do what's called conjugate transpose. The conjugate transpose of a matrix is defined notationally as writing A to the star. And this is obtained by first transposing the matrix, and then we conjugate all of the entries inside of our matrix. So for instance, here we have a 3 by 2 complex matrix. We're raising the matrix to the star operator, which means we are going to transpose, and then we're going to conjugate all of our entries. So when we transpose this 3 by 2, we construct a new 2 by 3, and then we're going to conjugate all of the entries in that 2 by 3. So this I plus 2 and 1 in the first row of the original matrix becomes the first column of the new matrix, but we conjugate each of those entries. So I plus 2 becomes negative I plus 2, and 1 remains equal to 1. Then in the second row of the original matrix, 17i plus 2, negative 9i minus 4, we rip that row out and place it in the second column of this new matrix, but we also conjugate those two entries. 17i plus 2 becomes negative 17i plus 2, and negative 9i minus 4 becomes 9i minus 4. Finally, the last row, negative I2, becomes the last column of this conjugate transpose, but again, we conjugate those entries. Negative I becomes I, and 2 remains equal to 2. So there's a word of warning we should issue here. Some people use different notation than A star. Many people write A to the H, and the H here stands for the name Hermite, who is the mathematician who invented this process. Other people use this dagger notation, so they write A to the dagger in place of A star. So be aware that other people use differing notation for the conjugate transpose operator. And another important thing to observe is that the matrices we've previously been working with, the matrices with real entries, satisfy the relationship A star equals A transpose, because we never change real numbers when we conjugate them. So what sorts of things can we say about conjugate transposition? Well, our first important theorem says that just like transposition, the conjugate transpose operation is another order reversing involution. What this means is that if we multiply two complex matrices together and then take the conjugate transpose, that's the same thing as conjugate transposing each of the matrices individually, but we now multiply them together in the opposite order. It also means that if we take the conjugate transpose of a matrix twice, we get back the original matrix. It's also what's called a conjugate linear operator. If we take a scalar C1 and multiply by a matrix A1, and then add that to a scalar C2 multiplied by a matrix A2, we can conjugate the result, and this is always the same thing as taking the conjugate of our first scalar, multiplying by the conjugate transpose of the first matrix, and then adding that to the conjugate of the second scalar, and multiplying by the conjugate transpose of the second matrix. And the conjugate transpose cooperates nicely with various operations on matrices, like trace, rank, determinant, and inversion. So we can make this more precise. The trace of the conjugate transpose of a matrix is always equal to the trace of that matrix, and then we conjugate the result. The rank of the conjugate transpose of a matrix is always the same as the rank of the original matrix. The determinant of the conjugate transpose of a matrix is always the conjugate of the determinant of the original matrix. And if we take the conjugate transpose and then invert, that's the same thing as the inverse, and then we conjugate transpose. For those who may not remember, I think there was a homework problem a while ago where trace was defined, but for the sake of completeness, let's define what trace actually means. The trace of a square matrix is defined as the sum of all of the diagonal entries. So the trace is by far the simplest of all the operations we've learned. To take the trace of a matrix, we just sum all of the diagonal entries together. Conjugate transposition also plays nicely with eigenvalues. It turns out that the eigenvalues of the conjugate transpose of a matrix are simply the conjugates of the eigenvalues of the original matrix. Another thing that happens with conjugate transposition is that we can move a matrix around inside of inner products. So if we want to take the inner product of a matrix A times a vector V with another vector W, the result is always the same thing as moving A to the other side, but when we do that, we have to conjugate transpose that matrix. So AV inner product with W is always the same thing as V inner product with A star times W. And this theorem is easy enough to prove. So if we're looking at the inner product of AV with W, by definition, that's the same thing as AV conjugate transpose multiplied by W. And since conjugate transposition is an order reversing involution, we can reverse the order of AV conjugate transpose to get V star A star times W. And now we can regroup our parentheses to obtain V star times A star W. And this is exactly how V inner product with A star W is defined. So what's the big point here? So we're doing linear algebra with complex numbers now. And the idea is that the work is almost exactly the same, except we have to pay attention to a couple of key points. When we're replacing R with C, we have to replace all of our dot products with inner products, and we have to replace all of our transposes with conjugate transposes. But after making these replacements, everything we've learned still works. So here we have a table of concepts where we will list a concept along with its formula in the world of real numbers, and then we'll state the analog in the world of complex numbers. So one of the fundamental constructions we've worked with is the Gramian of a matrix. The Gramian shows up in a whole bunch of our formulas, namely projections and least squares. And in the world of real matrices, the Gramian was A transpose multiplied by A. In the world of complex matrices, all we do is replace the transpose operator with the conjugate transpose operator, and we get the analogous formula. So when we talk about the Gramian in the world of complex numbers, we're talking about A star A, not just A transpose A. There's also the projection formula. In the projection formula in the world of real matrices, we take a matrix X, multiply by the inverse of its Gramian, and then multiply by X transpose. In the world of complex matrices, the formula is almost identical, except now we take X, multiply by the inverse of its Gramian, where the Gramian is obtained by taking the conjugate transpose and multiplying by the matrix, and then we multiply by the conjugate transpose of the matrix. So again, we're just replacing the transpose with the conjugate transpose here. Also, least squares plays the same way. The least squares formula in the world of real numbers is A transpose A x hat equals A transpose B. In the world of complex numbers, we simply replace the transpose with the conjugate transpose. So in the world of complex numbers, we work with A star A x hat equals A star B. And another fundamental fact about real matrices is that their a matrix has orthonormal columns exactly when it obeys the formula Q transpose Q equals the identity. Well, in the world of complex numbers, to check whether or not a matrix has orthonormal columns, we instead check the equation Q star Q equals the identity. Again, replacing the transpose with the conjugate transpose. Now, sometimes we actually change adjectives when we move from R to C, and there's a few key points we should make here. So remember that a symmetric matrix in the world of real matrices is a matrix whose transpose is equal to itself. Well, in the world of complex matrices, we don't use the adjective symmetric, we use the adjective Hermitian. So a symmetric matrix is defined by the property A transpose equals A. A Hermitian matrix is defined by the property A star equals A. Also, orthogonal matrices in the world of real matrices are matrices whose transpose are equal to their inverse. In the world of complex matrices, we don't use the adjective orthogonal, we use the adjective unitary. So an orthogonal matrix is a matrix whose transpose is equal to its inverse. In the world of complex matrices, we don't work with orthogonal matrices, we work with unitary matrices. These are the matrices whose conjugate transpose is equal to its inverse. So here are some examples. Here we're looking at two different matrices, and neither one of these matrices is symmetric. If we look at the first matrix here, this 18i is not equal to negative 18i. However, 18i is the conjugate of negative 18i, which tells us that this matrix satisfies the equation A star equals A. So this first matrix is an example of a Hermitian matrix. For this 3 by 3, we have more entries to compare. Here we're pairing negative I minus 3 with I minus 3. Those two entries are not equal to one another, but they are conjugates of one another. 12i minus 3 is not the same as negative 12i minus 3, but these entries are conjugates of each other. And 4i minus 12 is not the same as negative 4i minus 12, but those entries are conjugates of one another. So here on the right, we're looking at an example not of a symmetric matrix, but of a 3 by 3 Hermitian matrix, because it satisfies the equation A star equals A. Here we have another interesting example. Here we're defining a matrix Q to be 3 by 3, and all of the entries are 0 except 3 of them. In the 2, 1 position, we have the number I. In the 1, 2 position, we have the number 1. And in the 3, 3 position, we have the number negative I. If we take this matrix and multiply by its conjugate transpose, we turn out to produce the 3 by 3 identity matrix. This is exactly the equation we need to check to verify that Q star is equal to the inverse of our matrix. And when the conjugate transpose is equal to the inverse, we say that matrix is unitary. So this is an example of a unitary matrix. It's interesting to point out that this is not an orthogonal matrix, because if we multiplied this matrix by its transpose, we would not get the identity matrix. It is, however, unitary, because when we multiply this matrix by its conjugate transpose, we do get the identity.